Okay, so part two. This is part two of finding the area under a curve for this function right here. And so let me just show you the last time I did this, right? I broke this into this area under the curve into boxes, and I took the limit as the number of boxes goes to infinity, and I got an answer. So there's another way to do this. And that's with an integration. So let me just write this integration, and I'm going to skip some steps here. But let's say the area under the curve is equal to the integral from x equals 1 to x equals 2, because that's what I'm finding this from, of f of x dx. And so you could put in your function right there, and that would be cool and all. But let's look at this, and this is my short version of this. Suppose that I have this is my area right there, and then I move a little bit more, and I find a change in area. I'll call that dA. And this distance right here, let's call that as delta x, and this height right here is going to be f of x. So the area of the new piece, and this is a rectangle, it's an approximation, right? The area of the new piece, so dA is going to be f of x dx. I'm sorry, delta. I called that delta x. dA equals f of x delta x. So that's delta x wide and f of x tall. That's how much area I added. Okay, but now let's suppose that area is also a function of x, and as I go from here to there, I have this is area a of x. How big would that be? Well, that would be a of x plus delta x. That's the new area, right? I added on a little piece, I have a bigger area. It's going to be equal to the area a of x plus how much I just added on, which would be this part, f of x delta x. So now let's solve this for f of x. I get f of x. If I subtract a of x from both sides, so it'd be a of x plus delta x minus a of x, all of that divided by delta x. And now this is an approximation, but if I take the limit f of x is equal to the limit as delta x goes to 0 of a of x plus delta x minus a of x over delta x. That might look familiar. And this is really crazy if you think about it. And it kind of blows my mind. That's the definition of a derivative. So this says f of x is equal to the derivative of a of x with respect to x. Because that's what that is. So this says that the change in area is equal to the function itself. The rate of change of area is equal to the function. And that's what, like, wow. Okay, wow. So, but that tells us over here that if I want to find the area, if I want to go backwards, if I take the opposite of the derivative of this side, I get the area. So I have to take the opposite derivative of this side. So this means that the integration is an antiderivative. And that's like, wow. Okay. When we take that for granted, right? Because this, if I figure out what derivative gives me this function, then that's way easier than doing that summation notation that I did before. So let's do that. Let me write this out. There's another fundamental theorem of calculus that deals with limits of integration. I'll say this. The area equals x equals 1 to x equals 2 of f of x dx is equal to area at 2 minus area at 1. So you can actually do the limits of integration by doing the antiderivative, evaluating at those two functions, and taking the derivative. And I didn't derive that for you because, I'll run out of battery on my phone. Okay, so here we have the area is equal to the integration of x equals 1 to x equals 2. That's just I picked 1 and 2 because that's what I did before. And then my f of x was 3x squared plus 2 dx. So there's my function right there. And I want to say, what what would I take the derivative of and get that? And that will be my area. So we have this power rule, right, where we have something like this, c x to the n. And if I take the derivative of this with respect to x, then I bring down the n, so I get c n x to the n minus 1. That's, and plus, no, that's it. Okay. So that means if I want to do the opposite, then I'd add 1 to this. I wouldn't multiply by that number. I'd divide by it. So let's just check. So if, and the c doesn't matter. So if I say a of x equals, well, the antiderivative of this, I'm going to add 1 instead of subtracting 1, going the backwards way. So I'm going to add 1 and make that 3, and then divide by 3. So I get 3 divided by 3, x to the cubed. And we can check, right? What's the derivative of x? Let's write it out here. The derivative of x cubed with respect to x. Well, now I can use the same power rule, bring the 3 down front. I get 3. I reduce that by 1, x squared. And that is what I get. So that is the antiderivative. Now, what's the antiderivative for 2? What do I take the derivative of and it gives me 2? I again can use the power rule, because here I have x to the 0. So I add 1 and I get x. I divide by 1, so I get plus 2x. Now, you could add a constant in here too, right? But if I'm using limits of integration, I don't have to do that. So I'm just going to evaluate this from x equals 1 to x equals 2. So that means the area is going to be equal to this function at 2. So it's going to be x, not x, 2 cubed plus 2 times 2 minus this evaluated at 1, which is going to be 1 cubed plus 2 times 1. Okay, so this is going to be 2 cubed is 8 plus 4 minus 1 minus 2. So I get 8 plus 1 is equal to 9. And that's the same value I got before. That's the same value. Actually, look, I can even show you. I proved to you. See, look, here's my work from before. I did that, and I got 9. So, but this is a way simpler method to find the area under the curve rather than taking and breaking into all those pieces. But it gives the same thing. So that's this fundamental theorem of calculus. Okay. I did this one. Now I need to do that one. I'm going to do this with Python, and that's really the fun part, because that allows me to do something different. And I'll talk to you about that later.